Hello everyone, it's great to be with you in this digital form. I am Philip and I will be presenting the paper Deep Learning on Microcontrollers, a study on deployment costs and challenges. This is a paper by me, Javier, Edgar and Nick. Our association is with the University of Cambridge and Samsung AI. Despite the limited memory and compute resources, MCUs can be an attractive target platform for some DNN applications. In this work, we studied the difficulties introduced primarily by the lack of on-chip memory along with other residual factors. Notably, we elected not to use any of the existing MCU supporting DNN frameworks at inference time. This bare metal approach allows us to make observations without interference from the design decisions of any one framework. First, we'll discuss mapping DNNs onto MCUs. Then, we'll follow up with the discussion of working set, data movement, quantization, and high-level metrics considerations. Finally, we'll conclude with a set of lessons learned. A typical microcontroller is comprised of a processing core, on-chip static random access memory, and NOR flash memory where the program code lives. It is several orders of magnitude more resource constrained than today's average smartphone, especially in terms of on-chip RAM memory. On-chip RAM. From a computational point of view, a deep neural network is a sequence of linear algebra operations along with some element-wise nonlinearities grouped together into layers. The deployment of neural networks onto MCUs involves deciding where the weights, biases, and activations lie, how the compute operations are scheduled, and how the data gets accessed and processed. Executing a model that does not fit into on-chip memory could take the following steps for each layer in turn. First, load a binary blob representing the compressed weight of the layer into RAM from the storage. Second, revert any compression of weight, for instance revert Huffman encoding or k-means clustering. If the decompressed tensor does not fit into RAM, attempt to store it in the flash memory, or if it fails, onto the SD card. Then, execute the computation of the layer. Finally, store the result in a pre-allocated buffer in SRAM. This will become an input to the following layer. In order to assess how data flow impacts latency or energy consumptions, we studied the costs of the different types of data movement, data formats, and encoding schemes in detail. First, let me talk about DNN working set and MCUs. The working set profile of a DNN often displays significant variation across layers. Relative to the aggregate total model size, it gives a richer overview of the minimum resources needed to run a network. Figure on the left shows the working set of the baseline MobileNet, the standard in mobile sensing. We see that the working set exceeds the available MCU SRAM at the 6th and the 68th layers. The latter, even though serious, is less concerning since reading from an external memory source is much cheaper than writing to it. Thus, even though the network fails to fit in the SRAM at 2 points, only one of these failures prohibits realistic deployment. There is a fundamental difference between those layers whose working set sizes are close to the SRAM limit and those with working sets at comfortable distance from it. An experiment in the right figure demonstrates the impact of extra filters added to every layer at the baseline MobileNet. The top panel reports the increased working set size from adding 32 more filters to each of the first 10 layers. The bottom panel reports the per layer increase in forward path latency that resulted from this network expansion. The latency due to the added operations, these are the green bits, is dwarfed by those caused by writing out and storing of SRAM the excess output at layers 3, 5, and 6. These are yellow. And then reading it back at the next layer, pink. Note that layers 3 and 5 have only write-related latency penalty, as they exceeded the SRAM size themselves, but were not preceded by a layer that would do the same, and similarly layers 4 and 7 have read-only. Relative to these impacts, the other layers are affected only marginally, since the operation penalty is relatively small. For this reason, we omitted layers far away from the SRAM limit from these figures. In short, when networks exceed the amount of on-chip SRAM, they face a significant amount of data movement, which, as would be further studied, results in latency and energy penalties. Second, let me talk about data movement. The data movement costs are a function of the number of bytes to move and the position of the region or destination memory in the system's memory hierarchy. MCUs often rely on L2 SRAM chips as their main general-purpose memory. Bigger pieces of data can be stored on SD cards. Accessing these requires 2 to 3 orders of magnitude more energy than accessing the MCU's SRAM. At inference, each MAC requires 3 memory reads, 1 per buffer in the working set, and 1 memory write to update the output. Having an entire high-performance model in SRAM is not realistic. Therefore, in the worst case, each MAC requires 3 microSD card read accesses and 1 write. To provide some context, the reference MobileNet V2 model requires 300 million MACs per inference pass. Next, let me talk about the impact of memory hierarchy, flash reusage, and microSD card operation frequency. To demonstrate the memory hierarchy impact, we measured the latency and energy consumed while evaluating the last layer of our MobileNet V2 network when the weights reside in either SRAM, on-chip flash, or external microSD card. The input of this convolution layer is a 1 by 4 by 4 by 112 tensor, and the weights are of shape 1280 by 1 by 1 by 112. Retrieving the weights from microSD card results in almost 2 orders of magnitude increase in latency. When weights are either in SRAM or flash, latency is identical when measured as a resolution of 1 millisecond, but energy consumption is marginally higher when using the weights in flash. Next, we investigate flash reusage. In this experiment, we investigate the cost of offloading excessive working set onto the SD card. We measure the latency and energy required to store and read 1 megabyte of data in SRAM and the SD card. This is a realistic setup as inference would be performed multiple times on the device. We measure the cost of reading and writing such amount of data every 16 kilobyte blocks. In the figure below, we observe that while microSD card read-write is comparably costly, there is a big disparity between the costs associated to flash read-write operations. Consequently, it is only worth writing to on-chip flash during runtime if the data to be stored is planned to be used multiple times during network inference. Finally, we investigate the role of the microSD card operation frequency. From the previous experiment, we argue that it is preferable when needing to temporarily offload some data from system memory to use microSD card. In this experiment, we studied the impact in energy consumption that the operating frequency of the microSD card has in the overall system. We measure the energy required to write to microSD card arrays of different dimensions, resulting in file size ranging from 10 bytes to 200 kilobytes. In our development setup, we observe power consumptions of 460 milliwatt when setting the frequency to 100 kHz, whilst power goes up to 590 milliwatt when operating at the highest frequency supported by our system. Although higher frequencies translate into up to 25% higher power drain, the overall energy consumed suggests that using higher frequencies is more economical. Having discussed data movement implications, we move on to quantization, which aims to represent model parameters with fewer bits than the usual 32 used in training. There are three dimensions to it. First is the bit width, that is, what number of bits do we use in place of the usual 32. Common choices are 16, 8, or 1. Second is the granularity, which means whether we assign each weight, each layer, or the entire network the same precision. And finally, there is the implementation, where we consider the queue format, affine a codebook approaches. This figure shows an experiment where we measure the impact of performance of each of the quantization implementations on the MobileNet v2 0.35 network. The results verify that the simplicity of the queue format approaches results in lower latency, especially when exploiting SIMD operations compared to the alternatives. Codebook quantization underperforms significantly due to the low latency needed to compacted codebook. The affine quantization, similarly, requires longer processing times. And finally, we observe that regardless of the quantization implementation, there is a direct correlation between latency and energy consumption. Inherent to all of these quantization implementations is the need for additional parameters in order to give meaning to the quantized weights. Relying on high-level metrics such as model size or total number of megs needed for model inference could mislead the choice of architecture given an application and target platform, as these may not necessarily take into account all the costs associated with all these compression methods that were used to get to the particular number. Indeed, on the left panel, we show that high-level metrics alone might be misleading when assessing the suitability of a network or a compression framework for an MCU. We show that the stress in memory due to the sizes of the input and output tensors of a layer is far greater than that resulting from the tensors containing the weights. On the right panel, we also show that linearly increasing the model size does not necessarily translate into a linearly increase in latency. We can observe how other parameters of the hardware, in this case the amount of usable SRAM, significantly limits the throughput of the application when exceeding the maximum working set limit. Therefore, to make a model run at a reasonable level of accuracy, power use, and latency, the following are useful lessons. First, that the working set size likely becomes the main bottleneck. Second, the data movement costs significantly dominate over those associated to compute, and their minimization should be one of the primary considerations for a model designer. Third, quantization methods offer a range of different trade-offs in space of accuracy, bookkeeping, and implementation complexity. And finally, that high-level metrics that do not take into account the intricacies of the specific implementation, such as the bookkeeping and quantization, may mask many of the very relevant costs that the modeler would likely encounter. This concludes my presentation, and I thank you for listening.